Have you ever wondered how the design of a column is determined? Welcome to the fascinating world of column design where physics, art, and ingenuity come together in a harmonious blend. The design of a column is no random task, it's a meticulous process that involves determining the size, shape, and material requirements to create a structural column. This column must be resilient enough to support the load it's destined to bear, while maintaining unwavering stability and safety. A key factor in column design is the slenderness ratio, which plays a pivotal role in defining the column's performance under load. We also have to consider the type of load the column will carry. So, as you see, column design isn't just about aesthetics. It's about creating a robust, reliable structure that can withstand the test of time. Now let's dive into how we can calculate the load-carrying capacity of a column. The load-carrying capacity of a short column is determined by a simple mathematical equation. Let's dive right in. The load-carrying capacity is represented by P and is calculated by the formula P equals SSC multiplied by ASC plus SCC multiplied by AC. In this equation, SSC represents the stress in compression steel, while SCC stands for the stress in concrete. ASC is the area of compression steel, and ACC is the area of concrete. The area of concrete AC is calculated by subtracting ASC from the total gross cross-sectional area, represented by AG. So this formula is essentially adding the product of the stress and the area of both compression steel and concrete. This gives us the total load that our short column can bear. Now, you might be wondering why we differentiate between the stress in compression steel and the stress in concrete. That's because these two materials behave differently under stress. Steel is more flexible and can withstand tension better, while concrete is more rigid and better suited for compression. In the world of column design, understanding these differences and knowing how to calculate the load-carrying capacity of a column is essential. It's what ensures our structures are safe and durable. But remember, this formula is specifically for short columns. The calculation changes when we're dealing with long columns or columns with different types of reinforcement. These differences are due to the increased slenderness and potential for buckling, which we'll delve into in the next sections. So there you have it. By using this equation, we can determine the load-carrying capacity of a short column. It's a simple yet crucial calculation that forms the backbone of effective and safe column design. That's how we calculate the load-carrying capacity for a short column. But what about long columns? Let's find out next. Long columns have different load-carrying capacities than short columns. This is because the length of the column affects how much load it can bear without buckling or failing due to stress. To calculate the load-carrying capacity of a long column, we use a different formula than we do for short columns. The equation is P equals CR multiplied by the sum of SC times ASC and SCC times AC. Here the term P represents the load-carrying capacity of the column. The term CR is what we call the reduction factor, which takes into account the effective length and least lateral dimension of the column. This reduction factor is calculated as CR equals 1.25 minus the effective length divided by 48 times the least lateral dimension. SSC and SCC are the stresses in the compression steel and concrete, respectively. ASC and AC are the areas of the compression steel and the concrete, respectively. All these parameters are vital in determining the load-carrying capacity of a long column. The effective length, represented by the term LEF, is the length of the column that is free to buckle or deform under load. The least lateral dimension, represented by the term B, is the smallest dimension of the column in the direction perpendicular to the load. So, what does all this mean? Well, the load-carrying capacity of a long column is determined by the amount of stress the column can withstand, the areas of the steel and concrete that make up the column, as well as the column's effective length and least lateral dimension. This equation allows engineers to calculate the maximum load a long column can bear before it fails, ensuring the safety and stability of the structures we live in, work in, and rely on every day. And that's how we calculate the load-carrying capacity for a long column. But did you know using helical reinforcement can increase the load-carrying capacity? This is another important aspect of column design, and we'll delve into it in the next scene. Helical reinforcement can significantly increase the load-carrying capacity of a column. Let's delve into that. Helical reinforcement, also known as spiral reinforcement, is a method where steel bars are wrapped in a helical or spiral pattern around the longitudinal bars in a column. This type of reinforcement is particularly effective in enhancing the column's capacity to bear axial and lateral loads, and in preventing buckling of the longitudinal bars, especially in seismic-prone regions. Now, how does it work? Well, a column with helical reinforcement can increase the load carrying capacity by an impressive 5%. Yes, you heard it right, 5%. This might not sound like a lot, but in the world of civil engineering, every bit of strength counts when it comes to supporting structures. So, how do we calculate this? Let's break it down. For a short column with helical reinforcement, the load carrying capacity, denoted as P, is calculated using the formula P equals 1.05 times the sum of the stress in compression steel, represented by SSC, times the area of compression steel, ASC, plus the stress in concrete, SCC, times the area of concrete, AC. For a long column with helical reinforcement, the formula is slightly different. P equals 1.05 times the reduction factor, CR, times the sum of SSC times ASC plus SCC times AC. In both these calculations, the 1.05 represents the 5% increase in load carrying capacity that helical reinforcement provides. So why is this important? Well, by increasing the load carrying capacity of a column, we can design structures that are safer, more resilient, and more efficient. This is particularly crucial in areas prone to earthquakes, where the added strength can make all the difference. So, as you can see, helical reinforcement can be a game changer. Now let's talk about the longitudinal reinforcement. Longitudinal and transverse reinforcements are two crucial aspects of column design. Let's delve into the details. Longitudinal reinforcement, which runs vertically, plays a vital role in bearing the load of the structure. The minimum area of steel required for longitudinal reinforcement is 0.8% of the gross area of the column. And what about the maximum area of steel? Well, if the bars are not lapped, it's 6% of the gross area. But if they are lapped, the maximum area reduces to 4% of the gross area. The minimum number of bars needed for reinforcement also varies. In a rectangular column, you'd need at least 4 bars. For a circular column, the minimum number of longitudinal bars required goes up to 6. The smallest diameter of the bar that can be used is 12 millimeters, and the maximum distance between longitudinal bars should not exceed 300 millimeters. Moving on to transverse reinforcement, which runs horizontally. The diameter of the lateral ties, represented by the Greek letter phi, is determined by the minimum diameter of the main longitudinal bar. The pitch, represented by the letter P, is the minimum of the least lateral dimension, 16 times the minimum diameter of the main longitudinal bar, or 300 millimeters. But what about helical reinforcement? The diameters of helical reinforcement are selected based on a specific formula involving the gross area and the core diameter. The pitch of helical reinforcement should not exceed 75 millimeters, and it should be at least 3 times the diameter of the steel bar forming the helix, or a minimum of 25 millimeters. As you can see, both longitudinal and transverse reinforcements have specific requirements that must be met to ensure the stability and safety of the column, and by extension the entire structure. That's all about longitudinal and transverse reinforcements. Now let's wrap up. So, we have covered a lot about column design today. We've delved into the intricacies of determining the size, shape, and material requirements for a structural column, focusing on the vital role of the slenderness ratio and the types of loads on the columns. We've explored the load-carrying capacities of short and long columns, understanding how these capacities are determined through specific mathematical formulas. We've also discovered how the use of helical reinforcement can increase the load-carrying capacity by 5%. We've discussed the requirements for longitudinal and transverse reinforcements, including the minimum and maximum areas of steel, the minimum number of bars needed for reinforcement, and the specific dimensions for bars and distances between them. And we've touched on the importance of pedestals and the specifics of transverse reinforcement and helical reinforcement, and that's a wrap on column design. Remember, every column in a building plays a crucial role, and understanding their design can help ensure the stability and safety of the structure.